Hi guys, we're Drew Miller and Caelyn Sobie, and we're going to be presenting about Fermat's little theorem and Euler's theorem, which are used in number theory to make things easy.
Okay, so first we have to start off with the basic modular arithmetic. So basically, it just deals with remainders. Like, okay, so if you say A is congruent to B modulo C, it's just if A minus B, all divided by C, if it's an integer, then you can just say that, and you can also write it like that. And okay, so like for example, that's a little confusing. If you want to say like 31 is congruent to 1 modulo C, that's because so 31 minus 1 is 30, and then we know that it's a multiple of 10, because 10 times 3 is 30, so then that works. But like, it wouldn't be if like 91, you can't say like 91 is congruent to 18 modulo 6, because 91 minus 18 is 73, and divided by 6, that's not an integer. Here's a video for
Bob discovered something very interesting while making multicolored earrings out of beads for his store. Now his customers like variety, so he decides to make every possible style for each size. Starting with size 3, he begins by figuring out all possible styles. Well, each earring begins as a string of beads, and then the ends are attached to form a ring. So first, how many possible strings are there? Well, with 2 colors and 3 beads, there are 3 choices, each from 2 colors. So 2 times 2 times 2 equals 8 possible unique strings. And then he subtracts the strings which have only 1 color, or monocolored strings, since he's only building multicolored earrings. Then he glues them all together to form rings. He was assuming he'd end up with 6 different earrings, but something happened. He can no longer tell the difference between most of them. It turns out he only has 2 styles, because each style is now part of a group with 2 identical partners. Notice you can always match them up based on rotations. So the size of these groups must be based on how many rotations it takes to return to the original, or how many rotations to complete a cycle. So this means that the original set of all multicolored strings divides evenly into groups of size 3. Now, would this be true for other sizes? That would be convenient, since he always wants the same amount of each style. So he tries this with 4 beads. First, he builds all possible strings. And with 4 beads, he can choose from 2 colors for each bead. So 2 times 2 times 2 times 2 equals 16. Then he removes the 2 monocolored necklaces and attaches all of the others to form rings. Now, will they form equal-sized groups? Apparently not.
Will the
What
following
happened?
students please report to book
Notice how the
meeting?
initial set of
Eric
strings
Garcia,
divides into
Jordan
styles.
Gonzalez,
If strings
Adriana
are of the same
Hanna,
style, it means you can form
James
one into the other
Justin
simply by
Siegel,
grabbing beads from
Valentina
one end
Siegel,
and sticking
Thomas
them onto the
Koja,
other end.
Bethany Lopez,
And there is one style which
Santiago
only has
Martinez
2
Contreras,
members, and this is because
Jamie
it's
Martinez,
built out of a
Tammy
repeating unit of
Martinez,
length 2.
Naya Middlebrook,
So only
and
2
David
rotations
Ontiveros,
are
please report
required to
bookkeeping.
complete a cycle.
And also,
Therefore,
if
this
you
group only
purchased the
contains 2.
WOC card and did not receive
You
your
cannot
red
split
wave
them
shirt,
into an
can
equal
you
number of
please go to
styles.
bookkeeping? They have them in stock.
What about size 5? Will they break into equal number of each style? Wait. Suddenly he realizes he doesn't even need to build them in order to find out. It must work, since 5 cannot be made up of a repeating pattern, because 5 cannot be broken into equal parts. It's a prime number. So no matter what kind of multicolored string you start with, it will always take 5 rotations or beat swaps to return to itself. The cycle length of every string must be 5. Well, let's check. First, we'll build all possible strings and remove the 2 monocolored strings. Then we separate the strings into groups which belong to the same style and build a single earring for each style. Notice that each earring rotates exactly 5 times to complete a cycle. Therefore, if we glue all the strings into rings, they must split into equal-sized groups of 5. But then he goes one step further. Currently, he is only using 2 colors, but he realizes this must hold with any number of colors. Because any multicolored earring with a prime number of beads, P, must have a cycle length of P, since primes cannot be broken into equal-sized units. But if a composite number of beads are used, such as 6, we will always have certain strings with shorter cycle lengths, since it's actually built out of a repeating unit, and therefore will form smaller groups. And amazingly, he just stumbled onto Fermat's little theorem. Given A colors, and strings of length P, which are prime, the number of possible strings is A times A times A P times, or A to the power of P. And when he removed the monocolored strings, he subtracts exactly A strings, since there are 1 for each color. This leaves him with A to the power of P minus A strings. And when he glues these strings together, they will fall into groups of size P, since each earring must have a cycle length of P. Therefore, P divides A to the power of P minus A, and that's it. We can express this statement in modular arithmetic too. Think of it, if you divide A to the power of P by P, you will be left with the remainder A. So we can write this as A to the power of P is congruent to A mod P. And here we have stumbled onto one of the fundamental results in number theory merely by playing with beads.
Okay, so now we're on to Euler's quotient function, and it's that mess, but it's not that complicated. So this is just like this function is for like saying it counts the number of integers that are less than n that don't share any common factors with them, and then that like with p is p minus 1 if it's a term.
So, one thing, you might have noticed that we jumped around a little bit. This will come into play more when we talk about Euler's theorem, which is like the general form of, like, Fermat's little theorem is a more specific version of Euler's theorem, so we'll get to that in a second.
So like this is just like example of how it works. So like if you take 1,000, you take 1,000, and then you use the prime factors, and then you don't need to count the exponents. So like you would do 2 something like that. And then you take 1,000 and you multiply 1 minus 1 over the factor, and you multiply it again by 1 minus 1 over the other factor, and then you get 1,000 times this, and that equals 400. And then you do it again with the rest, and it'll again, and then for this one, you minus this one because it's going to tend to be n, it's not like the actual number. So you do the same thing, where it's times 10 to the n times 1 over, and then you take the factors of 10, which are 2 and 5. And then you also.
So basically, if you were to factor 100, you would have repeated 2s and 5s. That doesn't matter. All you do is you subtract 1 minus 1 over that factor, regardless of how many times it repeats.
Okay, and now this is Euler's theorem. So it's 1 to the a to the phi of n equals 1 natural n, and that's where n and a are co-prime positive numbers. And then so we use this theorem to make like really big numbers way less like smaller. We're using the properties of congruence, and so this is just like a generalization of Fermat's theorem. This is the actual theorem. So you use this one if it's prime, and then you use
You use Fermat's little theorem if the modulus is prime. So if it's a mod p, you would use Fermat's. If it's not, you would use Euler's Totient function. So now we're going to do some practice problems using these properties. So you might notice that we have like find the last 3 digits and the last 2 digits. That's because I just want to show 2 different methods of doing these. So the first one, you would find the last 3 digits of that big old number. To find the last 3 digits of a number, you're taking that number mod 1,000. Because if you were to like chop it off at like 3 decimal places over, what's left over, the remainder, would be the last 3 digits of that number. So we're looking for 7 to the 9999 modulo 1,000. So we're going to use Euler's Totient function. So phi of 1,000, as we did earlier, is 400. So because any number a to the phi of n is congruent to 1 modulo n, we know that 7 to the 400 is congruent to 1 mod 1,000. So now we can use this knowledge to apply it to here. So we know that 9999 is almost 10,000. So what we can do is we can multiply 400 by 25. And basically raise this to the 25th, which means we raise this to the 25th also. But since 1 to the 25 is still 1, we're left with 7 to the 10,000 is still congruent to 1 mod 1,000. Moving on, we need to find something that is also congruent to 1 that's divisible by 7 that'll help us make this go 1 lower. Because if you were to divide this by 7, it would be 7 to the 9,999. So this is relatively simple. 1,001 is divisible by 7, and it's congruent to 1 mod 1,000. Because if you were to just remove that, you have 1 left over. Okay, so we can factor this into 7 times 143. That's not exactly a simple thing, but it is a thing that works. So because this is equal to 1, or is congruent to 1 mod 1,000, and this is congruent to 1 mod 1,000, they are essentially equal to each other for all intents and purposes. So now, we have a 7 here, we have a 7 here. We can get rid of those, make that go down by 1. So 7 to the 9999 is congruent to 143 mod 1,000. So the last 3 digits of 7 to the 9999 are 143. Cool.
Cool.
Next one, the last 2 digits. So this one, I'm going to be doing it a little bit differently.
Make him guess a little bit, Joe.
Okay. What's up?
Well, like, what would be the mod?
Okay. Yeah. What would be the modulus? Because we used 1,000 here. So what would be the modulus here? 100. Yes. 100. 100 is correct. For example, if you were looking for the last 4 digits, you would take mod 10,000, and so on and so forth. But those get really, really long. I didn't want you to do that. So I'm going to be taking all these mod 100, these basic exponents. So that's 1. That's 7. That's 49. Thank you. but mod 100. So just 43. It would be 343, yes, but since it's mod 100, it's the last two digits, just 43. 7 to the 4. Whoa, that's 1. It repeats. Okay, so we can use that. We know that it repeats every 4 times. So we're back to here. Because we know that the exponents repeat every 4 times, we're looking for the exponent mod 4. So we can see that this is it's 1 away from 10,000 again, and 10,000 is divisible by 4. So because of that, it needs 1 more to reach 10,000. So this would actually just be congruent to 3, because if you were to add 1 to 3, you would get 4, which is in fact divisible by 4. So this is congruent to 7 to the 3rd, which is also congruent, as we did up here, to 43. We're done. That one. There's one more. There's one more. Anybody need this anymore? Cool. All right. Last one, we're actually going to use for mods this time. We're looking for this mod 11. 11 is prime, so we'll use Fermat's little theorem. So if you don't quite remember, that's a to the p minus 1 is congruent to 1 mod p. I'm assuming we'll post these on our website so you can go back and look at all these theorems later. So because of that, we have a, 4, and we have p minus 1, 11. Well, p minus 1 is not 11. P is 11. 11 is prime. So p minus 1 would be 10. A is 4. 4 to the 10 is congruent to 1 mod 11. We can check this on a calculator that can take this, if that's important.
The calculator is also on one of the slides.
Is it?
Yeah, you can put it on.
There was a link there.
Oh, okay. Yeah. All right. So now we know that 4 to the 10 is congruent to 1. So if we were to raise that to any exponent, doesn't matter what, it would still be congruent to 1, because 1 raised to any exponent is still 1. So because of that, we can break this off into 4 to the 530 times 4 to the 2. We did this because this is divisible by 10. So this is 1. So we're left with this mod 11. We all know that 4 squared is 16. 16 mod 11.
Hold on, let him guess.
Any guesses?
5.
Show me on your hands.
5.
There you go. 5. So, if you were to take this big old number and divide it by that little old number, because it's prime, we can use Fermat's little theorem. The remainder is 5. Cool.
Hold on, because I know it's going to ring real quick. Hold on, listen. For you people in here that are wanting to compete